Welcome to this NPTEL course on Advanced Pre-Stressed Concrete Design. We are now entering to the new module and it is on importance of external post-tensioning, particularly from strengthening point of view, and we will go through several case studies how external post-tensioning can be quite helpful in improving the performance. The learning outcomes, the student after going through this video should be able to understand what is external post-tensioning system and how they are used for strengthening applications, and what are the analysis and design considerations of external PT system, particularly from strengthening point of view, and they will also be able to get insights on different case studies illustrating the use of external post-tension systems for structural strengthening. Right. So, we typically go for strengthening a structural member or a system to improve its structural performance, namely strength, stiffness, ductility or their combinations, right. And we have broadly, we can classify the strengthening techniques as two types. One is a supplemental technique, that means whatever that intervention that what we are adding, it could be FRP composite that you add it for confinement or for external bonding for flexural or shear strength improvement or steel plate bonding. All these things will act as only as a supplemental reinforcing system. That means they will come into picture only when the structural element is subjected to more load than actually it has been there when you are applying this strengthening system, right. And typically they are less expensive, but primary systems are actually more expensive, and this here you are talking about a system that can engage and it will involve lot more interventions in a way that implementation also is going to be more difficult, and only with the external bonding of FRP or steel, which may not be possible, right. And another, in primary strengthening, we classify them as either as an active strengthening or a passive strengthening, right. So, or in other words, in active strengthening, right after the intervention that whatever that you have implemented, most likely it is some form of post tensioning that will help in engaging the load. However, in passive strengthening, mostly in the case of external bonded system like FRP or steel plate, these additional elements will come into picture only when it is being overloaded more than what it has been, the structural system has seen at the time of installation, right. So, here we are talking about active or passive, and most of the structural interventions are passive in nature. So, we will talk about that. So, we have two types, passive strengthening and active strengthening, and typically passive strengthening will need additional loads to engage that intervention, that what you have said, and whatever that is bonded to the concrete. But active strengthening can help in immediate stress reduction and engagement of the system. The reason is, whenever you put external bonding of FRP or steel plate, you do not release the entire load. That means the dead loads are always acting. Probably you can reduce the live load that it is acting while you do the intervention, but you cannot completely remove the dead load, right. Whatever the shoring that we do, we can only partially remove the effect of your dead load. You cannot completely remove the effect of your dead loads, and even some portion of the live load will also be active. So, that is the reason these interventions, they do not come into picture immediately after strengthening. It requires lot more extra loading to engage that new system that we have added. So, such systems are called passive systems, but active strengthening, in other words, it can help in immediate stress reduction, and the system will engage with the original structural system right after its installation, right. For example, this is what we said, passive techniques. It could be a fiber reinforced polymer bonding that we do either for flexure or shear, or a steel plate or a steel element bonding like this. All these things are help in strengthening the system and stiffening the system, but while the dead loads are in place. So, that means more than the dead load it has to see before these systems can be engaged. Similarly, concrete enlargement as well. So, all these, for example, you have a beam here with FRP steel plate or concrete enlargement, all these engagements are actually called as passive systems, and it needs more load, additional loads for engaging the new intervention that what we are doing into the original structural member. Now, again in continuing forward, so again passive system includes concrete jacketing, where you add additional thickness of the concrete with additional reinforcement, steel jacketing, that what you have seen here, and the CFRP strengthening that is commonly used. It's a contact based system, and FRP is basically trying to confine the concrete column to increase its axial performance. And then you have CFRP bonded as an external reinforcing system. Here in this case you have a strip that is added on the soffit as well as a U jacket that you have for shear. These are all called as passive systems, in addition to these kind of steel plate systems also. These are all called as passive systems, and these systems are not going to help in participating the load resistance right after their addition to the structural element, right. So, that is why they are called passive systems. Now, one more example for a passive system, you can see here that for additional strength and stiffness, several I sections have been added to this flat plate system, and you can also see here this kind of a steel corbels have been added. So, all these things are actually passive systems, right. So, now what is the need for active strengthening, and in which cases we go for active strengthening, right. As we have explained, it is going to help in immediate stress reduction and engagement, and whenever you have a problem with deflections in a structural system, it is the active strengthening that will help to relieve the deflection related issues, right. So, one of the very common strengthening technique that is used is an external post tensioning system. We have seen this, okay, this kind of a external cable that I can create, and then I can attach concrete elements. If you have a column or a beam, end of the beam, what I can do is I can put this external anchor systems, and of course, these anchorages have to be designed carefully. Anchorages to be designed carefully, right. So, you see here, then what happens while you do pre-stressing, we have studied the load balancing, right. Depending upon the pre-stressing that we engage in this external cable, and I can design this slope change in such a way that I can create this uplift force, which is basically P into sin theta from both sides. The total net vertical uplift is going to be 2p sin theta. So, this 2p sin theta can be designed, let us say this entire thing, if I sum them as 1 w, then I can design 2p sin theta in fact to be equal to w, and I can find out by appropriately choosing the amount of pre-stressing and the cable profile, I can completely nullify the total external load also. So, in this way we can create an uplift force to balance the external load depending upon how much you want to balance. So, now you can see right after this intervention, immediately it is helping in releasing the effect of your external load. So, in that way, that is why it is called as an active system, and typically whenever structural system is having problems related to deflection, this kind of active strengthening is what we try to engage. And we know how to design this using load balancing concept, right. So, we have studied in detail, and we also looked at continuous systems, PT flat plate system. In all these things, the fundamental principles remain the same. You design the cable profile in such a way that you try to balance at least some fraction of your external load, right. Right. So, post tensioning system can be used to create loads opposing to that of applied external loads. Now, the drape, that means the slope, and the PT force can be adjusted for the required performance like we had discussed. Another classic example is this. Let us say I have a roof, now I want to add some HVAC system and I want to put lot of heavy equipment, let us say on the roof slab, then you are going to have significant amount of external loads that are being added. So, that is going to create strength as well as deflection issues. Now, how do we address it? So, if I know the amount of load that it is coming, then I can design an external PT system, so that it is going to create an uplift force which is exactly equal or maybe higher than that of the new equipment. In this way, I can without much alteration to the size of the member, I can quickly put a PT cable, but of course, these anchorings have to be designed properly, and we need to make sure that by applying this PT force, we are not going to damage the existing structure. So, all those things have to be taken into account very carefully, but this kind of intervention is quite easy and very elegant in taking care of this new load requirements. Now, what is external PT? So, as you know, we have talked about pre-tensioning and post-tensioning, and in external PT, when we say the PT elements are always outside the element, because here we are talking about structural strengthening. The structures have been already constructed, and after certain period of use you have some problem, that means you can add only element outside the existing structural element. So, that is the reason we call that as an external PT. And again, post tensioning, you know, in post tensioning is a method of pre-stressing in which tendons are tensioned after the concrete is hardened. So, typically PT we do, and it is also kept external to the structural element, that is why it is called external PT. Now, again the concept is very simple. We are adding the PT cable outside the structural element if you are going only with external PT, but if you are combining them with concrete enlargement, still for a parent element it is outside, but then that can be encased with concrete jacketing also. So, the concept is very simple. We are stretching the cable, and then the cable in turn is going to create an opposite force on the concrete, and it is going to create an uplift force, right. So, using load balancing concept, and we know that RCC element will crack, and PT slab after the pre-stressing it is going to have a camber like this that we have talked about, and then after the load is become, the camber will get nullified and you will have some deflection due to service loads. So, basically we are trying to create a load which is going to oppose the effect of your external loads, because these PT elements are added to the structural element after that is being in service. That is why we call that as external post tensioning, and it is an effective method for strengthening and repair, and used irrespective of what material it is. It can be used for strengthening concrete, it can be used for strengthening a steel, and it can be used for strengthening a wood also. It can typically it is used for increasing the strength and help to reduce the deflection, and because most of the time external PT is designed to be unbonded, we can go back and re-stress if they are unbonded, right. And if they are bonded, of course, you cannot re-stress it, but for an unbonded cable I can go ahead and increase the pre-stress at a later point of time as well, right, because they do not have grout inside the cable, and you can actually re-stress it to the level what you want. Less time for installation, because it is quite easy for us to install as well. Okay. So, as you can see, external PT systems have tendons installed outside the structural element. One example is this, the beam that you have, and then you have bridge element that is like this. You can design the cable which are basically anchored with the deviator blocks in the cross beams. Okay, these are all cross beams. These are your primary girders. So, I can run the cable taking advantage of the configuration that is already there, right. And because it is external, we have the possibility of monitoring and replacing the tendons, and we can also have ease in concreting, and so we end up with better concrete quality, and we can also use narrower webs. and as we have discussed, it is the primary method for strengthening rehabilitation of existing structure, particularly which have problem both with deflection and strength, right. Because it is an active system, it can help in reducing the deflection significantly. What are the benefits of external post tensioning? As you can see, the size, it is not basically going to increase the size of your parent structural member too much. So, there is a minimal size increase. So, that means it allows for large loads with minimal headroom and non-disruptive installation. That means while the structure is being in use, we can go ahead and do the installation without really disrupting the building function. Lightweight, and you are not adding any extra concrete. If you are doing concrete enlargement along with the external PT, then you are adding some weight, but otherwise the weight of the cable itself is not going to significantly change the weight of the structure. So, no impact on existing structures, and as we have seen, deflection reduction. So, it is a only effective method for reducing the deflection, and enhanced durability, because we are applying additional pre-stress, it helps in minimizing the crack and increasing the durability, and we can design the system without really changing. Let us say you have a MEP systems, mechanical, electrical and plumbing systems. So, I can design a cable without really affecting much the existing MEP system, only very minimal some disruption will be there to change it, but otherwise I can design a system which is not really going to have conflict with the existing MEP provisions. Now, where all we are going to use this external PT for strengthening? We can use it to improve the strength, reduce the deflections, or most of the time it will be required both. And it can be designed as an external system or an internal system. How do you do that as an internal system? I put external PT, but then I can encase with concrete jacketing, right. That means the system here, you have this PT cable that is running, right. So, and then because I am adding an external concrete jacketing as well, now the PT cable will be embedded within the concrete. So, it becomes as an internal, as part of the original structural system. External is easy, but again fire and durability considerations are there. So, if you want to improve the fire resistance, then I have to go for some kind of a fireproofing that we need to do. Internal cores are trenches in the slabs, it can be for concrete encasing like what we have seen in the picture. Now, concrete enlargement for encasing the PT also is possible, right, and design of anchorage zones are very, very critical, because now we are adding a PT force by reacting against the member itself. I have to choose the locations where I am putting these anchors, and at that anchor locations you will have heavy stress concentration. So, we need to design those anchor zones very carefully, right. Okay, what are the other advantages in seismic repair? This is one classical example of a flat plate that failed in an earthquake. You can see car park failure in 1983. So, you can see here, for such kind of systems also for seismic shear, to improve the two-way punching shear failure are very common in flat slab. We have discussed that in the PT slab as well, and external PT along with shear collars can increase the punching shear strength and reduce the deflection. So, I can combine the shear collars along with PT system that can significantly improve the punching shear strength and the deflections related to flat slab system. So, the techniques for seismic repair are very similar to other types, and post tensioning can increase the two-way shear resistance significantly. So, I can run the cable in both the directions externally and then along with some shear collars to improve the performance significantly. And now, this also we have studied it in PT slab system. So, you can see here there is a reverse parabola, and if you just look at the free body diagram of the cable, to keep the cable profile, because of the pre-stressing force that I apply, the radial force what it is going to be generated is nothing but 8 into P into H2 by 2 beta L1 the whole square. So, now you see beta L1 is basically the half of the length of your reverse parabola. So, total length of the reverse parabola is 2 beta L1. So, you can see that P into H is your moment that we are creating. So, your radial force is nothing but 8 into PhD by 2 beta L1 the whole square. So, we have studied this previously. For one tendon, it is going to be like this. Now, for punching shear, why we are saying this is whatever the cable that are crossing within that shear perimeter, that is your force per unit length. I multiply by C1 plus D, this is your shear perimeter, right, in one direction. So, whatever the cable that are within that width of C1 plus D is going to help me in Vp component. So, this is your force per unit length multiplied by C1 plus D will give me the total Vp. So, this is the total Vp. So, we know that Vp is going to be adding to the shear capacity in addition to your concrete shear strength plus the pre-stress component, Vp component also will be added to the shear capacity. So, by adding pre-stressing cable at a proper profile, again I can increase your Vp. In that way, I am also increasing my concrete shear capacity.